So a part of our course project is about exploring the technique of Monte Carlo research, and we are going to demonstrate its application on a game of chess. So first, running the code. So let's say we select the algorithm MCTS, and for difficulty we select easy and color white. So we already have a chessboard printed in the terminal. And the way the chessboard is labeled is that from left to right we have labels A from starting from A B C D, and starting from the white's position we have numbers from 1 to 8. So number gives you the basically numbers give you the row number, and ABCD give you the column number. So suppose I have to move the black pawn that is on my cursor. So that is ABC and C7. So I move it from C7 to C6. So I type C7, C6. So I move my black pawn. Now it's the computer's turn. So we see that the computer has basically moved this WN piece. WN is basically the white knight. And suppose we also remove our knight. So black knight, this would be AB, B8 to A6. B8, A6. So now it's the computer's turn. So this is how the game will progress. Now looking at the code. So the code basically starting from the code basically uses the Monte Carlo tree search. So starting with the explanation of that. So MCTS basically will help our AI decide on the best move by simulating many possible outcomes. So it's basically a tree search. So there are 4 steps: selection, expansion, simulation, and backpropagation. In selection, we're basically choosing the nodes in a game tree. We're both balancing how many nodes to explore versus how many to exploit. And we're choosing nodes with the highest upper confidence bound. And after selection, we move on to expansion, where we basically expand the leaf node. So looking at the code, so we have the init function, which basically we're inputting the initial state of the game represented by a game state object, the number of iterations to run the algorithm, and an optional exploration constant, then the depth limit, and whether to use an opening book or not. The opening book is basically a set of uh, default moves, or a set of best moves that we know are best moves based on the domain knowledge in chess and lot of chess research done previously. So so after selecting the next node to explore using the upper confidence bound algorithm, we're simulating a game from that node, and then we're backpropagating the result of the simulation to the root node. So that algorithm is run for some number of iterations, and we select the best move based on the number of wins for each child of the root node. So looking at the functions ahead, so set current node basically sets the current node to the one corresponding to the given state. Then we have the select function, which will select the next node to explore. Then the expand function, simulate function, and the backpropagate function. And then we finally select the move based on our tree search results. In this, we also have the implementation of a hash table. So what does this hash table do is basically that it will store the results of the simulation. So we don't have to simulate the same game state multiple times. And we also have alpha beta pruning to speed up the game. And then there's a prime handler, which basically is used to generate the hash table. So we also have a CNN implementation. So most of the traditional chess engines in the past used to only use Monte Carlo tree search. However, today the world-class chess engines, for example, AlphaZero, they use a combination of MCTS and CNN. So we implemented a basic version of that. So typically, CNN is used for object detection and problems involving images. So over here, the reason we use CNN is basically that it will help us to understand spatial relationships between pieces. And thus, that would be helpful to identify threats and attacks on the board. And to propagate information further in the network, the filters are basically convolved over the image. Now, to basically pass a color image into CNN, we typically would split the image into color channels. So over here, we're splitting the chessboard into 12 component channels. And now 12 component channels, because each channel basically has information about the presence of a certain piece of a certain color. Now, since we have six different types of pieces like rook, bishop, knight, pawn, so there's six pieces and two colors. So which is why we have 12 components and so 12 channels. And each channel is basically like a 8 cross 8 2D vector. And that 2D vector is ones and zeros, ones indicating the where that where that particular piece is present on the board, and zero if that piece is not present on the board. So basically, this model is basically integrating the CNN model for predicting the next best move based on the board positions. And we're, as explained earlier, we're basically passing the board state into, we're converting that into tensors and helping the network to learn. And the CNN evaluates this current board configuration and it outputs probabilities for the like most promising moves. And these probabilities are used to make decisions. So as we can see in the code, we have the CNN class, and this CNN class basically is used to create the model, train the is used to create the model, train the model, save the model, and load the model as well as predict the results. And there are two branches. We have the board branch and we have the turn branch. And later, the both of the branches are then like merged, and they're passed through the series of layers. And then we combine the model we compile the model using the Adam optimizer and categorical cross entropy loss as well as accuracy metric. So we had trained this model for like 128 epochs and a batch size of 64, and we have the training set in like in this way. This is the FEN notation. And initially we had basically run the CNN script to train the model and save it in the cnn.h5 in the train model folder. So this was our model. Then we also have the chess class. The chess class basically ch- defines the game state wi- and also the pieces. So the pieces basically we're defining the characteristic and the movement rules for each pieces, and then other rules like for example this is the king piece code. So we have the get legal moves which will give me all the current moves that are possible, and when I input a move it will check the move if that move is actually something that could be executed or could be not. And then again for the king we also have to check if it is in check or not. So similarly for each piece we have defined the movement rules and some other special rules. For example, for the pawn we have like if the pawn can be promoted or not. So this was a project overall. Thank you.
And as part of our DA311 and DA322 project, I'm going to explain about one of the methods that I have used in our that we have used in our project, and that would be neurosymbolic methods. So we have did an application on neurosymbolic AI for visual question answering. It is a hybrid approach to artificial intelligence, which combines the strength of both neural network as well as symbolic reasoning. This integration is a significant leap toward building systems that not only perceive but also reason with precision, mimicking human intelligence more effectively. So let's start with a simple analogy. Imagine a child looking at a picture of a book. They first recognize shapes, colors, and objects, which is called perception in our term. Then they answer questions like how many red circles are there, which is what we call reasoning about these objects. This blend of perception and reasoning is exactly what neurosymbolic AI aims to replicate. Now let's go into its application, which we have worked on. It is called visual question answering, a field where AI answers about questions which are related to images. So it has mainly three different processes. So the first process is about the perception module. The perception module starts with an object detector which identifies and isolates objects in a scene. For instance, it can detect shapes like circle or rectangles and colors like red, green, blue, or orange. The next step is attribute extraction. Here, a convolutional neural network classifies these shapes and colors. For example, it may determine that one object is a red circle while another is a green circle. These attributes are then structured into a scene representation, essentially a table that lists each object's shape, color, and position. This structured representation transforms raw image data into a symbolic format which can be further used for reasoning. Now let's go into the second step, which is semantic parser. So the once the image is understood by perception module, the system processes the question. For an example, suppose the question is how many objects of the same shape as the red object are there, or which is the closest circle to the red rectangle. So we can use a transformer based model, which is basically a powerful neural network for natural language processing. It converts the question into a sequence of symbolic instruction. For example, the question may be parsed into filter red object, followed by query their shape, then filter object with the same shape, and count them. This symbolic breakdown links the language of the question to the image structure data. This process is further followed by program synthesis and execution. Using a domain specific language, the system executes the symbolic instructions step by step. For example, it filters red objects from the scene, it queries their shape, finding it to be a rectangle or not. It filters all rectangle, and finally it counts these rectangle to arrive at the answer. For an example, the question that we asked earlier was how many objects of the same shape as the red objects are there. So as you can see in this image, the red object is a rectangle, and the number of shape which are same to rectangle is 2, which is this one and this one in the image. So it would give the output as 2. This stepwise reasoning ensures transparency and correctness, which is a very good advantage of neuro symbolic AI over purely neural approaches. Neural networks excel at perception, handling raw, unstructured data like images or speech, whereas symbolic reasoning ensures interpretability, accuracy, and the ability to generalize from logical rules, which is very advantageous for a lot of applications. Thank you. Like to go through the code base of this neurosymbolic AI project for visual question answering. So the if I would go through line by line code, then it would take a lot of time. So I would be going through the pynb file where I have combined all those functions. So the first I have uh, called all libraries followed by dataset generation. For an example, here I have generated a sample using my build sample code, which has been imported from this data generator .py file. So this build sample creates an image, for an example this, which has circles and rectangles. It also creates question and answers for this image. For an example, what is the closest shape to the orange object? So the closest shape to the orange object is circle, and there are a lot of different questions. And after that, I have created the full data set for training purposes. Now first I will go through the perception module, which basically used for identifying and classifying different shapes in the image using a convolutional a neural network. So I have trained the model. I have trained the model, and you can see there are two types of object in my image, which is one circle, another one is rectangle. Here all the model has been trained. So so the pipeline for the perception module is basically detector, which detects attributes such as shapes and colors and extracts structure scene representation. You can see the structural scene representation here, which basically gives the shape, color, and position of different objects. For example, an orange color rectangle shape is being positioned at this location, which is 171, 172. The perception module is further followed by semantic parser, which basically which basically tokenize the different questions as being asked on the image using some natural language processing techniques, and is further used for answering those. And this scene in this semantic for and this semantic for the image is used for the answering those questions. So you can see these has been tokenized, and the words have been tokenized and has been and different questions are being assigned some categories. For example, what is the furthest shape of the green object is being categorized as filter green, relate furthest, and query shape. Similarly, all the queries are being tokenized and categorized to answer those questions, and then finally we have plugged everything together to train and test the data set. Thank you.